Bismillahir Rahmanir Rahim. Assalamu alaikum to the third lecture of Fundamentals of Electrical Engineering. Today we are going to talk about the fundamentals of electric circuits. Now, if you remember the last time we were talking about these two topics, some revision of electromagnetism and a very you can say small topic of rotational motion. Previously, in the before that, in lecture number one, we covered system of linear equations, complex numbers, and derivatives and integrals. These were the prerequisites that we would be using a lot in this course. Similarly, in lecture two, we covered electromagnetism and rotational motion. Today, we are going to actually formally start with the basic concepts of electric circuits. So, the first idea that one must understand is what is an electric circuit. So how do you describe an electric circuit? An electric circuit is simply a closed path that allows for current to flow in it. It's a closed path made up of conducting material. So I'm just going to write conductors, like different kinds of wires, and electrical elements. You know, the kind of elements like resistors, capacitors, and inductors. So this is the definition of an electric circuit. It can have a battery, for example. It can have some resistor, some capacitor, some inductor also. Inductor is also an element we would study. And these lines here, let me highlight them. These lines here, they are the conducting path. So they are used to connect these elements together. Such a closed path where electric current can flow is called an electric circuit. The second idea is what is an electrical element? I've used the term electrical element. What is an electrical element? So let me describe that here. So an electrical element is simply a two or three terminal device. A two or three terminal device that can be characterized by its voltage and current. Let me give you an example for that. So it can be characterized by its voltage and current. Let me write it here. What does this mean? First of all, let me tell you that most of the electrical elements that you are going to see, they are either going to have two terminals. You can think of terminals as legs. So for example, a resistor has two legs, a capacitor has two legs, but there are also some other elements like a transistor. This is a BJT transistor, and it has three legs. So an electrical element is a two or three terminal device that can be characterized by its VI characteristic, voltage current characteristic. For example, let's take example of resistor. So resistor, let's say one of its leg is A and the other is called B. So I apply some voltage VAB, and some current is going to flow in response to that IAB. Using both the voltage and current, we can find out the equation for resistor. You already know that equation, that's the Ohm's law. So the relationship between V and I, if you can describe it using an equation, any such device is called an electrical element. It has two legs, but some of them has three legs. So for example, if you talk about this transistor, let's call its leg A, this leg B, and this leg C. In a transistor, you can have three different voltages. So we can have VAB or VBC or VCA for a three-terminal device. And for VAB, you need to know the current entering the terminal A. For VBC, you need to know the current entering the terminal B. And for VCA voltage, you need to know the current entering terminal C. So this is what an electrical element is. A two or three terminal device that can be characterized by its voltage and current relationships. It can be two terminals, so then it would only have one voltage and one current. That's the easier of the two cases. And you can have three terminal devices where you need to have three equations that can completely characterize the device. If you cannot characterize any element, then it's not going to be considered an electrical element. You need to first get its equation. So with this, we have covered electrical elements. Now let's start talking about voltages and currents. So first of all, voltage. What is voltage? I think you already know that, but let me put the physics definition over here. Actually, voltage is the work done or energy required. So it's the work done or energy required per unit of electric charge. So per unit of electric charge. So actually, it's the work done. It's the energy that is given to just one electron. So dW, work done per unit charge, dQ. This is the voltage definition. It's nothing fancy. It's a very simple idea. By the way, when we are discussing voltage, let me clarify that voltage is also called sometimes you are going to see voltage written as EMF. Voltage is sometimes called EMF. EMF stands for electromotive force. Sometimes voltage is also called potential difference. And sometimes people simply call voltage difference. These are all names of the same thing. However, they have some context. So for example, if you have a battery like this is a AA battery, 1.5 volts. This is the positive terminal, this is the negative terminal. The voltage of a battery is mostly called EMF because it is such a voltage that can actually run any circuit. That this is actually a source of energy. Similarly, if you have a light bulb and there is some voltage across it, you are measuring that voltage, and that voltage is usually denoted by the term potential difference. It's not necessary to use these terminologies. You can simply call both of them voltage. You know the unit of voltage? Yes, you know that already. I think it's simply volt. Now, the next discussion in this regard is charge and current. We need to talk about charge and then how it flows to become current. Now, charge is simply the presence or absence of additional um, electrons in an atom. It's simply as simple as that. Presence or absence of charge in an atom. That's electric charge. You know that if there is an additional element and an additional charge inside an atom, so for example, you have an atom and there is an additional electron. If there is an additional electron, the electron, if there is an additional electron, then that kind of an atom is called a negative ion. Similarly, if there is an addition, you can say an additional proton, the kind of atom is called a positive ion. But there is a third possibility that the electron has become loose. So it has uh, just uh, it has just got out of the atom and it's now alone, and this is also considered a negative charge. So the positive ion is considered positive charge. You know that the negative ion is considered negative charge, and the independent electron is also considered as a negative charge. We are interested in this one because in electric circuits, the charge that flows is actually simply electrons. Now, you need to just remember a couple of facts about the charge of an electron. So, the charge on an electron, the charge is represented by Q. It has units coulombs. So, charge on an electron, I can write it like this. The charge of an electron is 1.602 times minus 19 coulombs. You must not forget to put a negative sign before this because the charge on electron is considered to be negative. Similarly, if we talk about the flow rate of charges, when the charges start to flow, that is considered current. And current is simply described as the rate of flow of electric charge. You know its unit also. Unit is ampere. And well, you can say that the current is considered. It's quite a debate actually. In the electrical scientists community, there is a debate that whether the electric charge is the negative electron or the positive ion. So there are two groups. Let me clarify that. Let me clarify this interesting fact for you, that current can be considered current in a conductor can be considered either as flow of electrons So you can think of electrons flowing in the conductor, and that kind of current, the flow of electron kind of current, is called electronic current. Some people say that current needs to be considered as the flow of electrons, and such a current is called electronic current. But some people say that it can be considered as flow of you can say it can be considered as, just hold on for a second. So it can be considered as flow of positive ions, and such a current people say is called conventional current. Now, both the definitions, both the methods of looking at the current are true. You can consider any one of them. In fact, we in this course are going to consider conventional current. Let me explain this through a diagram, that how both the currents are the same thing. Let's say you have this piece of conductor, you apply a battery across that, positive, negative, and now as soon as you connect this battery to this piece of conductor, electrons start flowing in this direction. You can see that every atom, let me let me draw some atoms for you here. So for example, these are a couple of atoms here. Now as the electrons start flowing in, let me use yellow color for electrons. So this is yellow color is an electron. The electrons start jumping from one atom to the other, and they go all the way to the other end of the conductor and come back here, complete the circuit. But at the same time, if you look what happens to the place where the electrons are jumping, look at that. So the same diagram, the same thing, the same piece of conductor, but and they are the same elements, the same atoms. So here are some atoms inside. So you can see that the electron is coming from here over here, and it's going to jump across the atoms. But when an electron jumps forward, what happens? The previous atom is left with a hole. So electron moves to the left, a hole moves to the right. In this way, holes are moving continuously from left to right. So when the electrons are jumping from right to left, holes are jumping from left to right. Both are a very good description of the motion of electric charge. This one considers electrons to be the charge carriers, and this description considers holes to be the charge carriers. Remember, they are not moving, both of them are not moving independent of each other. So when the electron is moving to the left, the holes are moving to the right. And hence, you can either take this definition of electric current or use this definition of electric current. Both are valid. The electronic version is called electronic current. When you consider holes, it's the kind of current is called conventional current. In the old days, conventional current was used because in the old days, earlier scientists thought that the flow of electricity was due to positive charges. They did not know about the existence of electrons at that time. They did not know about the existence of holes at that time. So they simply say that it's the flow of positive charges, which actually quite resembles the holes theory, and hence we can say we can still use the conventional current. So in this course, we are going to use conventional current. Nobody is going to ask again for electronic current. We can do that, but remember, you just need to revert the direction of flow of electrons. That's the only thing that's going to change. Every other thing is going to remain the same. So we are going to be using the conventional current method of analysis, and we are going to use our positive charges as the carrier of electric current. By the way, uh, we are talking about charges. There is a small concept I would like to discuss quickly, and there is another famous unit of charge. You see, charge is actually represented in coulombs, but in our practical life, there is something that we use on daily basis, and that is actually charge, but we don't really consider about that. So you remember that your mobile phone batteries or your car batteries have units in ampere hours or milliampere hours. These are battery capacities. Do you know what physical quantity these units represent? Ampere is current, right? And hour is time. So you are multiplying I times t. What is I times t? Let me show you. I equals dq by dt. And if you want to find out the charge, I can say dq equals integral I dt. Let's say the current is constant. In that case, what would happen is uh, q equals I integral dt, and finally q equals it. So dimensionally speaking, ampere times hour is same as electric charge, but the only difference is that we are using hours instead of seconds. If we were to convert the hour here into seconds, your battery capacity would be simply in coulombs. So there is an exercise. Let's say you have a mobile phone with 4000 milliamp hour battery. Do you know how much charge it contains in coulombs? Do this exercise. We are going to talk about it on the Google Classroom later. It's just simply swapping numbers. You can easily convert the units and let me know how many coulombs are there in 4000 milliamp hours. Now, the electric charge and current, you can see they are quite simple ideas. But in practical life, we don't uh, see the electric current in this way. In practical life, this is something about our practical life. So in practical life, we have something called AC and DC circuits. You know that DC is present in DC circuits are simply short for direct current circuits, and DC circuits simply are sources like battery or solar panels. These are the sources from where you can get DC, direct current. What is direct current? Well, it's nothing. It simply means that the voltage that you are using or the current that you are using, it doesn't mean direct current does not mean it's only for current. It can be for voltage as well. That's a kind of a slight inconsistency because engineers tend to use direct current and direct direct current for both voltages and currents. This is a slight discrepancy, but this is how the terminology DC is used. DC is used for both voltages and currents. So a DC voltage is simply a constant line of voltage. For example, your 9-volt battery. A DC current is simply a constant line of current. For example, 2 ampere current flowing in some circuit. So a DC voltage or a DC current is not going to change its value over time. They are going to remain fixed and constant. However, these DC circuits are slightly inefficient. And I'm going to talk about this inefficiency, and there is this assignment for you as well. It's not going to be given right now, but there is a documentary that I would like you to watch, and we are going to talk about the inefficiency of direct current. But there is an inefficiency, and due to that inefficiency, in the 20th century, some guy named Nikola Tesla said that instead of using these direct current and voltages, we should be using what is called an alternating current or an alternating voltage. So this is, for example, an AC voltage. Similarly, there can be an alternating current, AC current, and this can also be used to power electric circuits. In fact, we use them all the time in our homes. This is the modern method of using electricity, using alternating current. Now, there are certain benefits in using them. We are not discussing them right now, but let me just quickly write their mathematical form. So, for example, this AC voltage, which is a sinusoid, has a peak of 10 volts and it has a time period of capital T. Then I can write this voltage V equals 10 sine 2 pi 1 over capital T times T. Similarly, if this DC current is 5 ampere at the peak of the cosine and the time period for this waveform is capital T, then I can say that this current is 5 times cosine 2 pi 1 over capital T time period times T. This is how alternating current is expressed mathematically. Direct current is expressed in a very simple way. So you can say V equals 9 volts or I equals 2 ampere. Here we need to write an equation with voltage or current symbol. So these are the two kinds of electricities that we use. On our smaller circuits like your computer, your laptop, your mobile phone, they use DC, direct current, internally, and our bigger appliances like fans, refrigerators, and air conditioners, they use uh, alternating current. By the way, Tesla invented the alternating current systems. Do you know who invented the direct current systems? Do you know the name of the person who invented direct current system, DC generator and things? I think you already know Edison, Thomas Edison. So, um before I move forward, I am going to give you a small kind of an assignment, and that assignment is, let me write it here. I'm going to post a link on the group. That assignment is, you need to watch documentary which is from BBC. It's present on YouTube. You can easily search it. I'm going to post a link also. And the title of the documentary is Shock and Awe, the Story of Electricity. In a couple of weeks, I'm going to be posting an assignment based on this documentary. So you need to watch it, and the assignment would be uploaded hopefully by next week. And you would then complete the assignment based on this documentary. You are going to watch it and you're going to complete the assignment with the help of the knowledge from this documentary. So it gives you many answers. It gives you the answer to why you are using AC and why DC is not used. It's also going to give you many other answers, and it's a very entertaining watch. By the way, uh, you might be thinking, why is alternating current always sinusoidal? Well, it's not necessarily sinusoidal always. There are some circuits where triangular alternating current and square shaped alternating current waveforms are used. So this is AC, this is AC, and this is AC. We mostly use sinusoidal type in our daily lives, but that is not true generally. There are circuits which use triangular and square wave alternating currents and voltages. Now, uh, there is a quick discussion I would like to do, uh, and that discussion is interesting. You people might think in that way. Some of the students that I teach sometimes thinks in this way, and they ask, what is the speed of current or voltage? I have written a detailed description in the handout. You need to read the handout for this, but let me clarify this quickly for you. So, voltage is simply an electrical wave, and an electrical wave travels at the speed of light. So it's going to travel at the speed of light in your circuit. So let me quickly draw a circuit and will tell you how it looks. So for example, you have this battery, there is this switch, and there is this light bulb. And as soon as you switch this on, you turn this switch on, voltage spontaneously travels all across this circuit. So voltage travels at speed of light. Now, what happens is that this voltage is spread all across the conductor and all across this bulb. So what you should consider is that the voltage is going to be divided in small chunks. Let's call them delta V. So delta V here, another delta V here, another delta V here, another delta V over here, another delta V over here, another delta V over here. These are very small voltages, let's say 0.1 volt or 0.01 volt, and they are spread all across the conductor and all across the circuit as soon as you switch the circuit on. Remember that sum of all these delta V's is going to be 9 volts, since you are applying 9 volts. But this 9 volt is distributed in very small voltage fractions throughout the circuit. They are not the same, by the way. This delta V, for example, might be different from this other one. So they're not the same exactly, but they are very small voltages and they are spread in the circuit. And they are spread just as soon as you turn the switch on, because the voltage wave travels at the speed of light. Once this is done, in each of these small circuits, let me draw a boundary. Let's say this one. You can see there is a delta V voltage in this conductor. In this small piece of conductor, a current is going to be locally generated. Similarly, this other piece of conductor would have its own current generated, and every piece of conductor would have its own small current generated inside it. Hence, the current that starts flowing is much slower than the voltage. You might be amazed to hear that the speed of current in copper, for example, is of the order of 10 centimeters per hour. Yes, current slowly goes into the circuit, it turns around in the circuit. Actually, voltage is present spontaneously, but the current is moving very slow. And why can't you see the current moving very slow? Why does this happen that when you turn the switch on, the light bulb suddenly turns on? Because the voltage has already gone all the way to your light bulb, and inside the light bulb there is a delta V that is going to generate its own current. And that's why the light seems to be running spontaneously. It turns on spontaneously, even though the current itself is flowing very slowly. That's why I sometimes call that current is a local phenomena. Current is a locally generated thing. Some people have misconception that the electrons are going to come from this battery over here 9 volts, and then they would push the other electrons, and then those would push the other electrons, and this pushing is going to make the current go into the circuit. That's wrong. Actually, the voltage difference that's present across the piece of conductor would actually start moving its own electrons, not from those that are coming from the battery, but every small piece of conductor has its own valence, or you can say free electrons, which start moving inside them. They do not need a push from the electrons of the battery. So this is much more is written in the handout. Please go through that. I've given a detailed description on that. Uh, with this, I think today's lecture is complete. We are going to uh, continue with these topics, inshallah, in the next week. Hopefully, you are coming to the classroom. I am posting a feedback. You need to please complete that feedback about this course and how I am teaching, so that I can improve my teaching. Similarly, I would request you to watch this documentary. I'm going to post a link just below the Google Classroom classwork. You are going to see this, the link of this documentary on YouTube. It's a big documentary. I think it's more than 1 hour, but it's a very interesting watch. So please watch this documentary. We are going to talk about this documentary in the first live session next week. Hopefully, this is good for you. I'm also going to post a kind of a, you can say, a problem sheet, so you can start solving some numericals. They are very simple numericals at the moment. Later we are going to see some complicated numericals, but start working on the numericals. They are not assignment based, they are not due, but this documentary is due. So in the third week I'm going to be giving you an assignment on this documentary. So start watching this, start learning from these lectures. By the way, I forgot one very important thing. I did not tell you the course books that I'm referring to. So the book that I am referring in this course, let me write the name here. There are two books. One is Fundamentals of Electric Circuits, by Alexander. Just get any edition of this book. It's very fine. The second book that I am using in this course, and it covers only just 2 chapters. It's Electric Machinery Fundamentals, and the author is Chapman. I would try to share uh, some selected topics of these books with you on this Google Classroom. With this thank you very much. Have a good time on this Eid. We are going to inshallah meet after Eid. Thank you very much and Allah Hafiz.